Welcome to Chem Help ASAP. Let's learn about rate equations and reaction order. In the upper left corner, we have a very simple model reaction. A plus B goes to C plus D. How would we define how quickly this reaction is proceeding? Well, we might measure the rate of consumption of A or B, that is the change in the concentration of A over the change in time. Similarly, we might measure the rate of creation of C or D. We have some mock data in the upper right. In 1 minute, the concentration of C went from 0 molar up to 0.1 molar. The rate of this reaction over that time period was 0.1 molar per minute. So that's how we can calculate a rate. Great. What determines the reaction rate? Reactions follow rate equations. In the lower left, I'll show a rate equation. So rate equals a rate constant, that's K, multiplied by the concentrations of our different starter materials with exponents. So concentration of A to the lowercase a power and concentration of B to the lowercase b power. Let's discuss this a little bit more. The rate constant hides a lot of information. It takes care of things like temperature, the activation energy of the reaction, and other details of the reaction. Running a reaction at a different temperature or in a different solvent will affect the rate constant. How about these concentration terms? Each starting material is part of the rate equation. How much it affects the reaction rate depends on the exponent after that follows each concentration term. These exponents define each starting material's reaction order. For example, if lowercase a equals 1, then the reaction order of starter material A is 1, first order. If the concentration of A is doubled, then the reaction rate will also double for a first order reagent. The reaction order for each reagent can be 0, 1, 2, etc. Even fractional values are possible. In practice, we normally see values of 0 or 1 for each starting material. That's 0 or 1 for these exponent values. If you total all the exponents, you will know the overall reaction order. So there's a reaction order for each reagent and an overall reaction order. Let's make up a rate equation. So over on the right, rate equals K times the concentration of A times the concentration of B. For this rate equation, the order of A is 1. You don't have to write an exponent value of 1. And the order of B is also 1. The exponent value is 1. The overall reaction order is 2, simply the sum of all the exponents. So let's do another. Rate equals some rate constant times the concentration of A to the 0 power times the concentration of B to the second power. So in this case, the order of A is 0. Since any number to the 0th power equals 1, most people would actually simplify this rate equation. They'd leave A out of the equation altogether. If a reagent is 0th order in a reaction, then that reagent's concentration does not affect the rate of the reaction. That sounds weird, but it does happen, and it's fairly common. The reaction order of B is 2. Second order. So A is 0 order, B is second order, and the overall reaction is second order. While reactions can have an order greater than 2, second order is the highest value you generally encounter. So that covers the essential ideas of reaction rates, the rate equation, and reaction order. When studying a new reaction, chemists often use these ideas to determine a possible reaction mechanism.